Something is wrong with the sky. Not wrong in a small way, not a rounding error buried in a footnote somewhere. Wrong in a way that has some of the most respected scientists on the planet quietly admitting that maybe, just maybe, we built our picture of the universe on a foundation that doesn't hold up. And the strange part is, the machine that broke everything was supposed to confirm everything. When the James Webb Space Telescope launched, astronomers had a shopping list. They wanted to look further back in time than ever before, to catch a glimpse of the very first galaxies flickering into existence after the Big Bang. Nobody expected clarity to turn into chaos. Nobody expected the telescope to hand back images that made experienced scientists stare at their screens and quietly say, "That can't be right." But that is exactly what happened. Webb pointed its mirror at the deep past and found galaxies that, according to everything we thought we understood, should not exist yet. Not smaller versions of galaxies. Not stunted, half-formed clumps of gas struggling to become something massive, structured, almost fully grown galaxies, sitting in a universe that was barely out of its infancy. To understand why this is such a big deal, you have to understand the model we've been using to describe the universe for the better part of a century. Cosmologists call it the Standard Model, and it is one of the most successful frameworks in the history of science. It describes how the universe expanded from an unimaginably hot, dense state almost 14 billion years ago, how the first atoms formed, how gravity slowly pulled gas into clumps, and how those clumps eventually became stars, then galaxies, then everything else you can see in the night sky. This model isn't a guess. It's been tested against decades of observations, and it keeps passing. It predicted how much hydrogen and helium should exist in the universe, and it was right. It predicted the pattern of light left over from the early universe, a kind of cosmic fingerprint called the cosmic microwave background. And it was right again. For a long time, the Standard Model felt less like a theory and more like a settled fact. One of the things this model is very clear about is timing. Galaxy formation is supposed to be slow, painfully slow. Gravity has to gather gas across enormous distances. Gas has to cool down enough to collapse into stars, and stars have to accumulate in large enough numbers to build something as massive as a galaxy. According to the Standard Model, this process takes billions of years. A galaxy the size and mass of our own Milky Way should need most of cosmic history to fully form. So when Webb looked at galaxies that existed within the first few 100 million years after the Big Bang, the expectation was obvious. These should be tiny, faint smudges of young stars, barely holding together, nothing close to a real galaxy yet. Instead, astronomers found monsters. Some of the earliest galaxies Webb detected, existing when the universe was only around 5 to 7% of its current age, appeared to already have masses rivaling large modern galaxies. That is like finding a fully grown adult in a nursery meant for newborns. It doesn't just bend the timeline a little, it breaks it. A team of researchers, led by an astronomer at the University of Texas at Austin, ran the numbers on some of these early, unusually massive galaxy candidates and published their findings in a major astronomy journal. What they found was almost absurd. For these galaxies to have grown as massive as they appeared in such a short amount of time, they would have needed to convert nearly all of their available gas into stars almost immediately. In a normal, healthy galaxy, that conversion process is wildly inefficient. Out of all the raw material available, maybe 10% actually ends up locked inside stars. The rest gets blown away by radiation, heated until it can't collapse, or simply never gets the chance to condense. It's messy, it's wasteful. That waste is completely normal and expected. But these early Webb galaxies look like they were running at close to 100% efficiency, as if every single scrap of gas around them had immediately turned into stars with none of the usual waste. Nothing in our physics says that should be possible. It would be like a factory where every raw material that comes in the door turns instantly into a finished, sellable product, with zero scraps, zero delays, zero inefficiency. That doesn't happen in factories, and according to everything we know, it shouldn't happen in galaxies either. For a moment, this looked like it might be the crack that finally broke the Standard Model of cosmology. Some scientists floated the idea that maybe there were unknown particles or forces at play in the early universe, something that could kickstart star formation far faster than anything currently modeled. Headlines ran with the idea that Webb might have disproven the Big Bang framework itself. Then a more careful look started to change the story, at least partially. A graduate student at the same university in Texas led a follow-up study that dug deeper into these unusually massive early galaxies. What she found was that many of them weren't quite what they appeared to be. A significant number of these bright, seemingly overweight galaxies had something hiding at their center, a rapidly feeding black hole. When a black hole is actively pulling in huge amounts of gas, the material doesn't just vanish quietly, it gets compressed, heated, and accelerated to extreme temperatures before it falls in, and all of that violent friction produces enormous amounts of light. From billions of light years away, through the lens of a telescope, that light blends in with the starlight around it. the result is a galaxy that looks far more massive and far more luminous than it actually is, because a good chunk of that brightness isn't coming from stars at all. It's coming from a black hole, essentially lighting up its surroundings like a flashlight taped to a candle. These objects earned a nickname among astronomers, little red dots, because of their compact size and reddish color in Webb's images. Once researchers identified and removed these black hole-dominated objects from their sample, a lot of the extreme physics-breaking mass estimates came back down to Earth. The galaxies left over fit much more comfortably within what the Standard Model predicts. One of the researchers involved put it plainly. In terms of the Standard Model of cosmology, there isn't really a crisis here, at least not one caused by the galaxies alone. That should have been the end of the story. It wasn't. Even after stripping out all of the black hole imposters, there were still roughly twice as many massive early galaxies as the model expected. Not an overwhelming, universe-breaking number. Not enough to demand we throw out everything we know, but enough to make it clear that something about our understanding of early star formation is incomplete. One explanation gaining traction is that stars may have simply formed faster in the young universe than they do today. The early universe was denser and more chaotic, and in those cramped high-pressure conditions, gas might not escape as easily during the star formation process, allowing stars to form in tighter, quicker bursts than we see in the calmer, more spread-out universe of today. It's a reasonable idea, but it still means our models need real adjustments, not just a quick fix. And then, just when things seemed to be stabilizing, Webb found something else that made the picture even messier. Astronomers spotted a fully formed spiral galaxy, one with clean, organized arms winding outward from its center, existing when the universe was less than 2 billion years old. Spiral structure is not something that appears overnight. It requires a long, calm, orderly period of growth. Galaxies usually get their mass through violent mergers and collisions, chaotic events that shred any delicate structure before it has a chance to settle. Finding a mature, elegant spiral this early in cosmic history is a bit like finding a fully landscaped garden growing in the middle of a demolition site. One of the astronomers who helped identify it, based at a university in Australia, explained that there are only two real possibilities. Either this galaxy built its mass in an unusually smooth, orderly way, or it formed the vast majority of its stars right where they sit, without the usual chaotic pileup of collisions. Both explanations require rethinking assumptions that have stood for decades. To make things stranger, a separate team using Webb studied hundreds of galaxies from roughly the same era and found the exact opposite pattern. Most of those galaxies were messy, turbulent, and disorganized, exactly what the Standard Model would predict for that period of cosmic history. So now we have a universe where, side by side in the same slice of time, some galaxies are behaving exactly like the textbooks say they should, while others look decades, maybe centuries, ahead of schedule. That's not a small inconsistency. That's two different stories being told about the exact same moment in cosmic history. If that were the only oddity, it might be manageable, but there's more. A separate study, published in a leading astronomy journal in late 2025, and involving researchers from some of the top institutions in the world, looked closely at the shapes of many young galaxies Webb had photographed. What they found was that a striking number of them weren't round or spiral, or even irregular in the usual chaotic sense. They were elongated, stretched out like cosmic cigars, long and narrow in a way that doesn't match what the leading dark matter model predicts. This detail might sound minor compared to a galaxy being too massive or too organized, but it might actually be the most important clue of all. The dominant model of dark matter, the invisible material that makes up most of the universe's mass and acts like a scaffolding that guides where galaxies form, predicts that galaxies should generally clump into more rounded, web-like structures. Elongated, stretched-out galaxies don't fit that prediction well at all. What they do match, surprisingly well, are alternative models of dark matter, ones where the underlying particles behave differently, creating smoother filaments of structure across the universe, filaments that gas and stars can flow along in long, stretched-out streams rather than clumping into rounded shapes. If that turns out to be correct, the implications go far beyond a handful of oddly shaped galaxies. Dark matter isn't a side character in cosmology. It's the scaffolding the entire model is built on. It decides where galaxies form, how tightly they cluster together, and how the largest structures in the universe are arranged. If the nature of dark matter is even slightly different from what we've assumed, that difference doesn't stay contained. It ripples outward into nearly every prediction cosmology makes, changing the expected mass of galaxy clusters, altering how smaller satellite galaxies distribute themselves around larger ones, and shifting how gravity bends and distorts light from distant objects. You can't quietly swap out the foundation of a house and expect the walls to stay exactly where they were. So where does all of this actually leave us? It's important to say clearly that the standard model of cosmology is not dead. It isn't even close to dead. It still explains the leftover light from the early universe with incredible precision. It still correctly predicts how much hydrogen and helium exist across the cosmos. It still accounts beautifully for how galaxies cluster together across billions of light years of space. No competing idea comes anywhere close to matching that track record. But cracks are appearing that simply weren't there a decade ago. Massive early galaxies that shouldn't have had time to form. Fully organized spirals sitting right next to complete chaos in the same era. Long, stretched-out galaxy shapes that fit better with alternative ideas about dark matter than with the model everyone has trusted for a generation. None of these individually topple the standard model. Together, they're starting to feel less like isolated oddities and more like symptoms of something we haven't figured out yet. And this isn't even the only tension shaking the field right now. There's a separate, ongoing disagreement about exactly how fast the universe is expanding today, with two completely independent methods of measurement refusing to agree with each other, no matter how carefully scientists check their work. There's also a quieter puzzle about exactly how clumpy the distribution of matter in the universe actually is, where direct measurements consistently come in slightly below what the model predicts. On their own, each of these might be dismissed as a technical quirk. Taken together with what Webb is showing us about early galaxies, they start to look like different cracks running through the same wall. None of this is really a story about failure. It's the opposite, actually. This is exactly what it looks like when a scientific field pushes right up against the edge of what it knows, using the most advanced tool ever built for the job, and finds that the edge is further away and stranger than anyone expected. Cosmology has been here before. Back in the 1990s, the field faced a contradiction that seemed impossible to resolve. Measurements suggesting the universe was younger than some of the stars living inside it, which made absolutely no sense. That crisis wasn't solved by throwing out everything scientists knew. It was solved by discovering something new entirely, a mysterious force now called dark energy, responsible for accelerating the expansion of the universe. What looked like a fatal contradiction turned out to be the shadow of something enormous that nobody had detected yet. That's usually how these moments work in physics. They feel in the moment like an ending, like the walls are closing in and everything we've built is about to collapse. And then, more often than not, they turn out to be the opening of a door nobody knew was there. Right now, we are a species standing on a small, rocky planet, circling an unremarkable star, in the quiet suburbs of an ordinary galaxy, using mirrors, math, and a telescope parked a million miles from home to argue passionately about whether galaxies grew up too fast, whether the universe is expanding a few percent faster than it should, and whether the invisible scaffolding holding everything together behaves the way we've assumed for 25 years. There's something almost funny about that, if you step back far enough. And there's also something genuinely remarkable about it. We built a piece of technology precise enough to catch the universe contradicting itself. And instead of panicking, scientists are doing exactly what they're supposed to do. Checking the data again, questioning their own assumptions, arguing with each other in journals and at conferences, and slowly, carefully narrowing down what might actually be going on. More tools are coming that should help sharpen this picture even further. Future space telescopes designed specifically to study the expansion of the universe and the distribution of galaxies across huge volumes of space are already being built or beginning their missions. Ground-based observatories are producing increasingly detailed maps of the early universe's leftover light. Every one of these instruments adds another data point, another angle, another chance to figure out whether we're looking at a handful of unrelated coincidences or the first real evidence of something fundamental that we've been missing all along. For now, the honest answer is that we don't fully know. The universe is handing us pieces that don't quite fit the picture on the box, and instead of forcing them into place, the best scientists in the field are doing something harder and more valuable. They're sitting with the discomfort of not knowing, and they're letting the evidence lead them, even when it leads somewhere unexpected. The universe probably isn't broken. It's almost certainly just bigger and stranger than our current map of it. And if history is any guide, whatever explanation eventually comes out of this mess of massive early galaxies, mismatched spiral structures, and oddly stretched shapes, it's going to be more interesting than anything we could have guessed sitting here today. Thanks for watching, and I'll see you in the next one.